Oh, so now bin is here. Good. So I'll record. Yeah, I still have a little bit of a problem with my display. So I'm going to not go into full view mode. I hope this thing is big enough for you. Okay. So I know that if I go on, so I might go back and forth into this mode. Okay, let me see. Okay. So, okay, first, before I start ReluPlex, I want to give a gist of why simplex is a correct procedure, why it terminates and gives the correct answer. It will not be a formal proof, but it will just hopefully give you an intuition as to why it is correct. And I also in the process want to point out, see, for this, for simplex, as I might have told you, I'm using these two references, okay? Actually, chapter 5 in the decision procedure book, whose content itself is pretty closely follows this paper, which is a very accessible paper, which I found, okay? For simplex, okay, by these authors. Okay? So the pseudo code as well as the correctness argument are and its proof are fairly nicely given in this paper in chapter 5 of the decision procedure book, from which this example is drawn. Okay, that is from chapter 5. And as I said, chapter 5 itself is based on this paper and follows that structure. Now, for ReluPlex, which I'll be discussing today, the paper that I'll be using is this one. I've already uploaded that to Moodle. If I'll be uploading it later on. I'll upload this as well as the other paper. Now there are some differences, kind of notational differences between how the simplex itself is presented in this paper versus the way it is done here and the way that we have seen. So I want to first clarify, illustrate those differences, and then I'll come back to summarizing the correctness argument, and then move on to describing ReluPlex, which is a specialized decision procedure, an extension, so to speak, of simplex for dealing with feed-forward neural network with Relu. So what is the difference? Okay, so you see that here's how I presented the the procedure, the simplex procedure, okay, earlier. Whereas in here, in the ReluPlex paper, it presents it as a set of inference roots. One of the main difference is, whereas here it uses pivot and update. You pivot and then you update. They kind of combine into a single operation in this procedure. There it is presented as a set of inference roots, and that the pivot and update are separated, are kind of split into two separate operations. And sometimes this, presenting it as inference rule has an advantage, okay, in that you can explore different strategies and so on, whereas here it explores a particular strategy. So I want to, point that difference out. What exactly is happening? Okay, for those who are not familiar with inference rules, you should read each of these rules as if the condition following, given above the horizontal line. Each rule has a something, above a horizontal line and below. So if the condition above the horizontal line is met, then you apply, you do the operation, take the action given by what is given below the horizontal line. Okay, that's how it is. It's done. So the update is, as you can see, the update is always done on a non-basic variable. And as before, it is done when it is done. I'm sorry, it is done. So okay. Let me start with the pivot operation. So you do a pivot when a basic variable, violates its upper or lower bound. Okay, so that can happen. Yeah, so it has a bounds violation. So a variable has to be in the basic set, and either it is less than the lower bound or greater than the lower bound. Then you pivot it with a variable in the with a non-basic variable. And there are two ways of doing it. I mean, you will have to pick a non-basic variable which has some slack, okay, which has some slack, such that you can actually adjust it to bring this basic variable, which is out of bounds, to its bound, either lower bound or upper bound. And that's how, and that is exactly the condition that is specified here. As you can see, because they are combined here, you will pick, so you pivot it, by using one non-basic variable which has a suitable slack to fix the bound violation of the basic variable. Okay. After that, you update. Okay. You pivot it, and then you update all. The update always happens on the non-basic variable, and that's how it's done. Even in the procedure above, when you do pivot and update, that's how you do. Okay. So there'll be, after the pivot, one basic variable will be leaving the basic set and moving into the non-basic set. Okay. And then one variable with a non-basic set will be moving to the basic set, and that's what is done here. Okay, so as part of the pivot operation, you just move the variables from a basic to non-basic. After that, the updates all the variables in the non-basic set. Okay, the one that just now entered will obviously be set to its lower or upper bound, and all the and then there is implicitly, although it does not specify it in here, implicitly, since the pivot operation also changes all the equations, all the variables, the rest of the variables that remain in the basic set will have to be, their assignment will have to be adjusted as per the new equation. So that is not explicitly stated here, okay, but that also happens as part of the update operation. Okay, so that's how it is. And of course, there is a separate inference rule for determining the failure and the success. Okay, you succeed, you exit the procedure with a success using this inference rule. Okay, if every variable both in the non-basic set and basic, are within their bounds. Then you declare it to be SAT. And at any point, if you the variables, if there are variables in the basic set which are out of bound, but you cannot find any non-basic variable with a suitable appropriate slack to fix the out-of-bound violation of the chosen basic variable, then you declare a failure. Okay, so that's how it is done. Okay, so of course in this, so whereas here in the inference rules, I mean, the order in which you apply is not explicitly stated. It seems like it gives you more flexibility in the way that you apply. For example, you can keep on flipping. I mean, you can keep on pivoting, and then you do an update. But the standard strategy that is used by simplex procedure is, after every pivot, you do an update, and that's why, because that is the standard strategy that is used. That's why in the procedure in the pseudo code shown about here, they kind of merge the pivot and the update operation. So this exposition that is given as these inference rules, of course, it allows a little bit more flexibility in terms of the way that you apply. But the standard procedure is you do a pivot and then you do an update. Check if it is success or failure. If not, then you go back to fixing the bound violation of one of the basic variables. Okay, and so on. So to illustrate how you can view the simplex procedure in as application of these inference rules, I will take the same example that I showed you to illustrate the pseudocode on this the pseudocode procedure on these inference rules. So before I do that, I want if there are any questions about these inference rules and what I just now explained. Okay. Any questions? I mean, you can ask questions. Okay. And you can stop and then do. I mean, as long as I'm not completely lost, even if I'm completely lost, you can actually stop and then ask me to explain it again. Is it clear enough? Shall I go ahead? Okay. All are there. Okay. So let me. Yeah, take the same example. See, another difference is that, so the normal form in which you put, you remember that the way that the procedure in the decision procedure chapter is described is, it assumes that you introduce a new additional variable, these, which are shown as S1, S2, S3, for every term that applies. Okay, so what happens if there are constraints on the program variable like X and Y? See, in the example that I showed before, it so happened that there was no constraint on X and Y, which are the input variables. Okay, so you could have constraints on them. In this case, all the constraints, the bound constraints, the X and Y were completely unconstrained, and the bound constraints were only on these complex expressions, linear expressions involving them. What happens if you had, okay, the assumption in the way it is described in the paper as well as the chapter is that you would, if there is some constraint on X to begin with, on these variables, then you will have to equate them to a new additional variable. and express the constraints only in terms of those additional variables. Okay, that is kind of superfluous. I mean, it's redundant because you can always that unnecessarily introduces more variables, and this way of doing it by splitting these operations has that advantage. And that's why in this example, I have deliberately used, there are all these original constraints, but there is also an additional constraint that x has to be greater than or equal to 2. Okay? Greater than or equal to 2. And that is something that I have expressed here. Yeah, and the state of the simplex procedure in the way that it is described in the ReluPlex paper is exactly what how I've shown here. Okay, every variable, the variables are listed in this table. The variables are listed in the top row, and with the non-basic variables at the beginning and the basic variables at the end. So to begin with, the basic set includes all the additional variables, and there's a lower bound and upper bound on each of these variables that never changes during the procedure of during the simplex procedure. What changes are the assignment made to the variables and the members of the basic and the non-basic set. Yeah. So if you say in the earlier form, if there was such thing, so in this case, x has some bound constraint and y is unbounded, and as usual, S1, S2, S3 as before have certain bounds as they are indicated here. Okay, and they are given here as lower and upper bound. Now, normally, what will happen, what you would have done if you were doing the in the previous presentation is you would have introduced a fourth additional variable, equating that to x, and giving the constraint on that additional variable, and keep x as unbounded. Yes, the question? Was that a question? No. Okay. Yeah. Whereas here you don't need to do that. Okay. So, but the procedure is right in the beginning, because you can do the update on any non-basic variable. So right at the beginning, because these are all what you have, these program variables. I mean, the whatever variable that is a non-basic set, they're like independent variables. You can always set them, right? So you could do update operations on all these the non-basic variables, the program variables, right at the beginning, to set them to their lower and upper bound, which you would have done in the other procedure after pivoting. Whereas here you could do that, and then you start adjusting the thing, and that's what. And that's how you will see that we will be doing. Okay, so what I'm going to illustrate is the same procedure, the same example, with the additional constraint that x has to be greater than or equal to 2 by means of applying the inference rules. Okay, what I've shown here, okay, are the equations on the side and all these bounds. So obviously, x, you're starting with the initial assignment of 0 to everything, which means that the non-basic x, the input variable x is out of bounds, and therefore you'll have to fix that. Okay, so that you will do by using an update operation, by bringing x to its lower bound. Okay, by changing the assignment to 2. Okay. That as soon as you do the update, obviously all the the basic variables will have to be updated as well, because as per the equations, as I said, that happens automatically as soon as an update operation happens, and that will get S3 violate out of bounds. Okay, but this is, since it's just an update operation, not a pivot operation, the equations remain the same. Okay, and so now you start. So whenever there is a basic variable which is out of bound, and the only way that can be fixed is through a pivot operation. Okay, so you pivot. Oh, I'm sorry. Okay, I'll have to. The thing is not visible, so I'll go enter full screen here. Okay. Okay. So yeah. So first, X is out of bounds. It's non-basic. If it is out of bounds, and you update X to 2, and that's what is the result of doing that is shown in that table. Okay. Now S3 is basic. And it is now, S3 is a basic variable and is out of bounds. The rest are okay. And if it's a basic variable is out of bounds, the way to fix it is using the pivot operation. You pivot S3 with Y, okay? And, and in the moment you pivot S3 with Y, because all the rest are satisfying. So what you're there is from 0, 0, 0, you get to this this point. Okay, you get to this point. I mean, after pivoting, you will all change the equations, and Y gets set to 2, and so you so the pivot operation sets S3 to its limit, which is 1. Okay, and then you update all the Y becomes basic, and now you set. And now that ends that. Now this is if for a particular variable ordering. There is also if the variable ordering was such that your X was before Y. Here, in the previous case, of course, you will have to be using the variable ordering. Okay, even with these inference rules, you will be using a strict variable ordering. So there, I assume that Y was before X, because X is also a possible option to fix the outer bound violation of S3 here. But what if X was lower in the ordering with Y? Then you will end up pivoting S3 with X, which will change the assignment as shown in this table. That will actually end up moving from A. So in the first, when you pivot Y, you will move directly from here. Okay, from here you will be moving to where? To something like B, A to B, and then you'll be moving to the intersection of X equals 2 line with S3. Whereas here, with the variable ordering with X equal to Y, you will be moving from A to this point D, which is the intersection of S3 with the X-axis. And after that, you will be moving to the right solution. Okay, you will slide on S3 and get to the point where the intersection point, okay, of X is equal to 2 and S3. Now, the question that you could be asking is, this is relevant for understanding the correctness. Is it not possible, for example, with after you pivot S3 with X, is it not possible for you to, because the solution point is, in this case, is the two points of intersection of X is equal to line with S3 or S2, okay? So, in this case, we terminated with X is equal to 2 with S3. So the region that is shown here with X, with this new constraint is a subset of this shaded region here, okay? x is equal to 2 goes like this, and it is all the region above that x is equal to 2. So the question I'm raising is it not possible for one to keep pivoting back and forth between the same pair of variables? Because that is what, okay, prevention of that, ensuring that that condition doesn't happen. Okay, why not? See, when you are roaming around, when simplex is exploring all these points, these extremity points, these intersection points, as I call, which are not solutions. Okay, see, is there okay, good, Digant. Yeah. So, so is it not possible to keep pivoting back and forth? Okay. Now that is, see, that happens if you can keep on, for example, in this case, you move from A to D or A to B, and then you move back and forth, then, simplex may never terminate. It has to be making progress in the sense that in some sense has to be moving closer to a solution point. The reason that why is this not possible? Okay, and you will see the reason that thing is not possible is because after you flip S1, S3 with X, the variable that moves to becomes non-basic, that from basic to non-basic, that variable S3 in this case is always set to either its lower bound or upper bound. Okay. Now, and X is adjusted in such a way that it helps move S3 to lower and upper bound. Now, if in order for S3 to flip back into the thing, look at the condition. Okay, if you look at the condition in which this rule is applied, it has to be, you see, you pivot only if the slack variable, if the slack variable is either the slack variable, that is the non-basic variable, is strictly less than its upper bound or greater than its lower bound. Okay, since the one that got just flipped, the basic variable that got flipped, is set to either its lower bound or upper bound, so this condition will never get satisfied, and therefore, so in this case, in X, so S3 is set to 1, okay, and therefore it is never possible to pivot for it to move back immediately back into this into the basic set, because the one that gets pivoted out of the basic set will always be set to its lower or upper bound. So that is a very important observation that one needs to understand about the condition for precondition for pivoting, and that's why you'll never be able to keep flipping back and forth. That is important for termination. The other important point is, which I will so that, and the other, okay, so here is certain other observations. Okay, so if there is an LP, if there is a solution for an LP problem, you might have already observed that thing. See, it always produces a solution with the following structure. Okay, some subset of the variables, specifically as many of the variables that are in the non-basic set, are always set to what I call as these extremity or intersection points. They are always, there will be some subset of the variables that are set to either their lower bound or upper bound. Okay, all the rest of the variables, when there is a in the solution that simplex finds, are then variables. Then they are set according to the equations. Okay, according to the equations, because all the variables in the non-basic set, okay, that are non-basic, when the procedure terminates, will be set to their lower and upper bound, and all the rest of the variables will be in the basic set. They are dependent on the non-basic variables, so they'll be set as per the equation dictates. And the number of such possible, what I call is intersection point solutions, are finite. Okay, because the intersection points are all finite, because they're only a finite set of subset of those variables. And therefore, in other words, since there is always such a solution where the subset of the non-basic variables, and some subset of the original, all the set of all variables will be at their will be set to their lower and upper bounds. So there are only finitely many such possible solution space that simplex procedure will be exploring to find the thing. And that is another thing that is important to ensure that it terminates. Okay. Now, so in other words, so the lower and upper bounds are fixed, and the solution that it eventually finds is where one in which a subset of the subset whose size is the size of the non-basic set, and they are at these points, and therefore what happens is it needs to be the number of states, okay, where a state, the number of states that simplex procedure will be exploring itself will be finite. Okay, and so a termination itself can be guaranteed, and that's by ensuring that there are no it doesn't loop between two states forever, and that's how the termination argument reduces to. Okay? Another observation that you will have to that simplex about the simplex procedure is that simplex always satisfies this the following important invariant. Okay, that every n satisfies its bounds. Maybe right at the beginning, at the initial in the initial state, it may not be. As I told you, first you will you'll always update all the program variables which have bound constraints on them right at the beginning to bring them to their bounds. After that, after every pivot and update operation, this invariant will be satisfied, where every variable in the thing satisfies its bounds. And not only that, then it satisfies its bounds, and every variable in that non-basic set is set to either its lower bound or its upper bound. Okay, and yeah, so those two are important. First is that there exists such if there is a solution at all, a solution where the subset of the variables are set to their intersection point exists, and and this invariant is always preserved. With these two things, you can get to the understanding the gist of the proof of correctness of simplex. The first part of correctness is to show that it is soundness. What does that mean? The part one is whenever simplex terminates with a yes answer, the assignment it finds is indeed a satisfying solution to the LP problem. So this is guaranteed by the invariant and the terminating condition, okay? Because the invariance, ensures that every variable, every non-basic variable satisfies its bounds, and when it terminates, it only simplex procedure terminates only when all the variables are within their bounds, which means all the basic variables are within their bounds as well. If any of the basic variables are not within their bounds, of course, you will continue to pivot. Okay, and that's what this thing is. So when simplex terminates with a no answer, so the other part of the soundness argument is when it terminates with a no answer, then the LP input instance must be an unsat instance. So this is shown once again by showing that simplex will eventually get to explore if there is because if it's unset, if there is a way to fix it by pivoting, it will get to every possible pair of variables that are possible candidates for pivoting. Okay, in any given ordering, it can always, if there is a chance for pivoting, it will always pivot. It will always pivot. So as long as this part, ensuring this part of the soundness argument, as well as this can be ensured by termination, as well as the completeness argument, which says that for every LP instance, for every LP instance of the problem, that the simplex procedure does terminate. Both these things are guaranteed by ensuring that it terminates. Okay. Now, how is this shown? So I've already shown that. I already argued that you cannot be pivoting between, this thing is shown by, is guaranteed terminate if it does not recur, okay? If the same, if two states do not recur during the same state, as I argued, I mean, it explores only the number of different possible states since the simplex procedure explodes. For finding a solution is finite. Therefore, as long as it is the same two states doesn't recur in the exploration, it terminates. And how is this shown? That during an exploration, either it doesn't flip the same pair of variables twice, okay? That I showed that it cannot happen immediately, but maybe it will, even if it does not happen immediately, it may pivot with some other variables and later on flip with the original variable. That might happen. But if it does, that is two variables that were both in the basic set, come back into the thing. But even if that happens, it turns out that it will happen with not with the same variable assignment, okay? Because the variable assignment is also part of the state, okay? And for any given set of variables in the basic set, in the non-basic set, the possible assignments that it explores is also finite, okay? And therefore, the formal proof shows that indeed these two, even if the same, the pivoting brings back the same point, it makes you come back to the same two pivoting points, that it will happen only with a different possible variable assignment. Okay, and that's why, and that is how it is shown. Now, this is not a complete proof, and this needs you to do a proof by induction. And the paper that I showed you a reference to has this. Okay, but I hope I gave you a gist of the procedure. The main thing is that there are only finitely many possible states that a simplex explores, because every solution is within those finite possibilities, as I shown, and that as it explores, it never loops back to the same state. Okay, so those two are the argument that I give. Okay, so any questions? Okay. Okay, so it's 5:37. So let me then, yeah, this I've already shown. Why immediate flip is not possible, that I've already shown. But in order to show that you cannot have a transitive flip, that you flip with some other variable and then you bring back the original variable back to the basic set, when that happens, the variable assignment would have changed. Okay, and the possible different variable assignment that it explores is also finite, because it only explores those solutions where non-basic variables are being set. I mean, some subset of the variables are being set to either the lower and upper bound. That's why these possible variable assignments that the simplex procedure explores is also finite. Okay? And that is what gives the thing. So if there are no questions, then I will go on to motivating ReluPlex. Okay. Okay, so I will do it just by using this very simple example. Okay. As I said, ReluPlex is a specialized decision procedure that extends simplex with a few extra additional inference rules to take care of these ReLU constraints. To see what the problem is, of verification, satisfiability problem in the presence of ReLUs for deep neural network. Let me use this example. So here is an example. This is an example that is given in the paper, the ReluPlex paper that I gave you a reference for, that I will upload to Moodle. So here V31 is actually equal to V11. As you can see, if it is non-negative, if it is positive, then it just sends the same thing. Okay, even if it is if it is negative. Oh, I'm sorry. Okay, yeah. So as long, okay. So the question is, if it is possible, if it's negative, then it'll it'll be 0. Okay, and 0 will be propagated to the thing. So in other words, if the input is between 0 and 1, the output is, the question I'm asking is, if it is possible that the output is between 0.5 and 1. It is, obviously possible, because if it is positive, it gives the same output, and if it is between, and if it is 0, it'll be 0. So here I'm asking the question: if it is possible, if it is between 0 and 1, that this is satisfied. Okay, as long as V11 is 0.5 or above, then this is this is possible, and that's why this is satisfied. I suppose that is the property, whether as long as the input is constrained to be between 0 and 1, if the output can be between 0.5 and 1. That is the property that you want to verify. Okay. First, I will motivate by showing you why you need a ReLU, a specialized decision procedure. I already argued in earlier lectures that you can always model DNN as well as the properties that you want to verify of this kind in SMT logic and throw it at an SMT solver. Okay, and I also showed you a naive algorithm for solving such problems. And so you could do that. I'll show you that again for this example. So here, so so we have as shown earlier. So in order to use this model, the the hidden layer nodes are split into a a backward and a forward node for each ReLU node. So the backward node takes the linear value of the linear transform, and the forward node is the value at the forward node is the application of ReLU up function on the backward node. Okay, so that's how I've done, and as shown before. So you, in this case, the linear transform, the constraints expressing the linear transformations are fairly simple. So V2B, V21B has to be equal to V11, and V22 is just -1 minus V11. That expresses the linear transformation, the result of linear transform on this thing. And then similarly, V31 takes the value of the forward ReLU nodes and expresses the value of V31 in terms of those two things. Okay, which in this case is that -1? This should be plus. I'm sorry. This should be plus. Okay, so I thought so. Yeah, there's a mistake here. So that should be a plus. Okay, and then there are these constraints that express the ReLU constraint, as which can be done only by using a conditional thing. But V1 is greater than 0. If it is greater than 0, then V21B and V21F should be equal. If V2B1 is less than or equal to 0, then the forward node, the value at the forward node has to be equal to 0. And that there'll be one ReLU constraint for every pair of ReLU. Okay, and then you will have to then also encode the property that you're trying to verify, which in this case has to express the linear, the constraints on the input. So the question that you're asking is if this is satisfied, that as long as the input is constrained to be 0 and 1, is there a value such that the output can be between 0.5 and 1, which can be expressed as asking if there is a satisfying, if this entire formula is satisfiable, okay, in the SMT logic, the theory of so with arbitrary Boolean combination, because you have ReLU, that's why you have this is not an LP problem per se, and so you have to use an SMT SMT solver for this purpose. So what does that is where I was I'd shown you, just to give you the context. Shoot, did I have that? Yeah, so remember that I showed you this. One way is to just throw these formulas into an SMT solver, which uses an LP solver and takes care of all the Boolean combinations, okay, in the way that I showed you, okay. And then the event essentially boils down to doing a k-split, okay, on these conditions of whether the variables V2, V21 of B, the backward variables, are less than or equal to 0 or greater than 0. Because the functionality of the value of that is depends on that. Now, one way to reduce this into multiple LP calls is by making decisions on splitting that into two different instances of LP. So one where V21B is greater than 0, or V22B is or the other case where less than or equal to 0. For example, so there are two ReLU nodes here, and therefore there will be 4 possible such cases that you will have to consider. Okay, so for example, if the case where the ReLU 1 condition is negative and the other one is negative, so both are not active, in which case if it is less than or equal to 0. So the active case is when it is less than or equal to 0. The non-active case. The active case is when it is greater than 0. If it is less than or equal to, if both of them are non-active, then when you apply that, this will obviously one of the the conditions simplify and reduces that into an LP instance. Okay, which is what you will have to do in order to reduce that into an LP problem. Of course, you will have as many, because this is not the only case. We'll have to consider all the other cases, all the other possible cases. In this case, there will be 4 possible cases. Okay, and so the number of LP calls in worst case is exponential in the number of ReLU nodes, because the number of cases that you have to consider is exponential in the number of ReLU nodes. So the real and the other one that I showed you. Okay, this one. So what is that? Okay, so this problem, when you throw, when you throw it at the SMT, it has lots of heuristics in order to ensure that maybe you don't need to split, use the worst case kind of a thing. But after all, this is, so the real, either use SMT, in which case you'll have to rely on its internal heuristics. So the question is, that ReluPlex is addressing is if there is a way to extend this, and whereas SMT solvers does this for arbitrary Boolean a structure about this linear arithmetic, but in this case, since we are only interested in ReLU, the if then else structure, the conditional structures are fairly limited, and therefore the question that it addresses is if there is a way to reduce these case splits, that is by doing it only when it is necessary, okay, such that it won't explode exponentially in in a lot of cases. Okay, of course it's worst case exponential, and therefore you are bound to hit that that case in some cases. Okay, whether you use ReluPlex or not, but the motivation for a special purpose procedure is exactly this. Okay, is there a way to extend simplex such that you can do this thing? So here we reduced it into an LP problem by eagerly splitting, considering all the cases right in the beginning. Whereas what ReluPlex does is, it does it in a lazy fashion. Okay, it tries to postpone the case splits as much as possible and sees if it can use LP problem on an over approximation, on an LP instance that denotes an over approximation of the original problem, and then get away without case splitting. That is the central idea that ReluPlex uses, and you see this is where over approximation becomes important. Okay, so it and we'll see how that is it's done. Okay, let me go back to full screen mode. So what do I mean the over approximation? I'll express the over approximation And the over approximation, really what it does is it ignores, okay? See this, it ignores these ReLU constraints, okay? Completely. I mean, except for, yeah, so it assumes that if you remove these constraints, then you can see that this becomes an LP problem, okay? This is the ReLU constraints are the reason that it is not a conjunctive, not an LP, okay? So that's what it starts with, okay? And that's what I have expressed here, okay? So you'll see. So you start with, I'm doing this, I'm expressing this without the ReLU constraint as an LP instance in the format that we used, okay, in the tabular format, okay. So let me take you through this thing, okay. So variable, so as usual, so V11 has, yeah, so these are all the variables and all the, you know, the linear, you know, transformation, okay, the linear, you know, the functional dependency of the backward nodes on its input nodes. They are expressed as linear expressions, right? And as you know, that are in normal form to convert in the LP problem, all those things are assigned, are put as part of the tableau, okay, by equating them to a new additional variable. So the additional variables here are A1, A2, and A3. Since here there are no constraints on any of the you know, hidden nodes, and that's why the lower and upper bound. So there is one equation for every linear expression defining the backward ReLU node, okay, that expresses this in this case, and that's what A1, A2, A3 do. And since they are just equations and there are no bound constraints on them, I'm sorry, the bound constraints, since they are strictly have to be equal, therefore the bound constraints are the lower and upper bound are set to 0, okay, right? Because they are just equal. Now, in this case, the only constraints that you want to check are either on the input or the output variable. Okay, so that's why, and that is expressed. That's a linear, once again, linear constraint in this case. So that is expressed in terms of by specifying the lower bound of V11 to be 0 and the upper bound to be 1. Similarly, what you want to check is if the upper bound, I mean, if the lower and upper bound of V31 is between 0.5 and 1. That's why I set the lower and upper bound to 0.5 and 1. And you can see here that the only constraint imposed, so there's actually no constraint, there's no constraint, relating the output of the ReLU with its input. Okay, the only constraint that is imposed is that the value at the forward node has to be non-negative. Okay, that is the only constraint that is modeled here. The fact that when the backward node is greater than 0, the two values at these two nodes are equal, and when it is less than or equal to 0, when the backward node is less than or equal to 0, that the forward node is 0, that is completely thrown away. Okay, and therefore pretty much the backward and the forward nodes of a ReLU, those pairs, the backward and forward variable pairs corresponding to ReLU node are pretty much independent. Okay, are independent, and that's why the satisfying, this is an over approximation. That is, the number of satisfying solutions for this is more than the actual satisfying solutions for the original problem. But by throwing away that nonlinear dependency between the forward and the backward node, you are, by creating this over approximation, you are reducing into an LP instance. So you start with, and this is the over approximation that I start with. Okay, so yeah. So I want to make sure that you all understand why this is an over approximation, because after all, if you throw away some of the constraints, as I explained, you know, the number of satisfying solutions is larger, okay? And that's why it is considered as an over approximation. So now you check. Yeah, so that's the starting thing. Now you solve this over approximated LP instance that is an over approximation. If no solution exists, if the LP call returns with no solution, then obviously the original problem, there cannot be any solution for the original problem. Why? Because the original problems, the set of solutions for the original problem is a subset of the possible solutions for this over approximation. That's why you can return unset. Okay? Suppose there exists a solution for this over approximated network. Okay? And suppose that solution is alpha. Obviously, that solution may not. It's a solution that is derived by ignoring the ReLU constraints imposed on this forward and backward variable pair corresponding to ReLU. Therefore, you cannot declare it as a satisfying. So you have the problem of checking that indeed, that if the ReLU constraints are preserved or not. And that's what you see the DPLLT, the naive solution for DP for the SMD solver does by going back and forth. Okay, whenever it finds a solution for the Boolean network, it checks. You have to check the satisfying solution meets the ReLU constraints. And that is what is done. Okay, what ReluPlex at a top level does. So if there is a solution for the over approximated network, if alpha solution ReLU, okay, and how does it check that? It checks if the assignment to for every pair xi xj ReLU pair, it checks if it meets the ReLU constraint by just checking if the assignment, assignment to xj, the value of xj is max of 0 and xj. That is the ReLU constraint. If the nonlinear constraint is expressed here as in terms of max. Okay, that you'll have to check for every pair. Okay, if none of the if that is met by every ReLU pair, that is, if none of the ReLU constraint is broken, then you can return. Then the satisfying solution is indeed a satisfying solution for the original problem with ReLU constraints. Okay, if not, what happens if it is not, if the one or more ReLU pair constraints on ReLU constraint is broken, then you need to, it has certain new way of updating. Okay, in addition to the usual update that you saw in for simplex, and that update, it tries to fix the forward and backward nodes of the offending of the ReLU pair that is broken, the broken ReLU nodes, by setting by updating F or B in such that it fixes the broken, it makes it satisfy the ReLU constraint. After that, but when you do that, there can be other variables which get out of bound, and therefore, So you'll have to go to, after fixing that, you know, and we'll show you. I'll show you how the special update rules to fix that. So since you could have driven other variables, driven them out of bounds. Other variables means such as the other, you know, I mean, yeah, because they have. So you go back and then run LP, okay, LP instance after fixing that, okay, and you keep doing that, okay, and if yeah, until you either satisfy it. So otherwise, if it's not possible to, if you've tried, you know, fixing a certain number of times and you still cannot do that iteration between step 5 and step 2 doesn't succeed even after a certain number of times, then you give up, okay, and you perform a case split, which is always a backup solution. The hope here is that this procedure of fixing and rerunning the LP on the over approximated thing, that is how you delay the need for a case split, okay? And the hope is that maybe you can, the property that you're checking is such that you can just run, you know, you can just find a solution with the, you know, without any case splits at all, or at least postpone it until you really need it. Okay, that is the essential idea. So to summarize, two ideas. Okay, you start with an over approximation of the original network by ignoring the constraints, all the nonlinear constraints imposed by the ReLU nodes. That allows you to get the thing into an LP instance, and then you keep you know, add new update rules to fix the broken ReLU pips. Okay, so you know, now I'm going to show this on this, how it works, illustrated how it works on this particular example. Okay. Okay, so this is the starting point. Is there any question in the modeling itself? If you have not understood how I modeled this, the notation, or why it is an over approximation, you'll have to ask questions. Okay, since there are no questions, I'm going to assume that you understand in what sense this one is an over approximation of your original network. Okay. So as an input-output behavior, this has more possible, permits more possible behaviors than the original network, because it is throwing away some the ReLU constraints on F and B. Okay, so this is what I start with. Okay. So I was just showing you what this. Okay, I think I'll get to this later on. What does case split do? Okay, and I think I'll get to that later on. So I will. No. I should. Okay. No. Okay, let me start with this. So this is the starting over approximation. Okay, so I'm starting with all you know, the assignment that gives assigns value 0 to everyone. I mean every variable, and obviously this one in this assignment. V31, the non-basic variable V31 is out of bounds. So you can, that is at the right the beginning, as I told you, that yeah. So yeah, so that updates the input variable v31, okay, to its lower bound, and that makes A3, which is dependent on v11, to go out of bounds. Okay. So you pivot that with one of the variables that can fix it. So which in this case is v21 of f. Okay, and you pivot that with that to get this one. Okay. So v21 of f will get set to 0.5, and A1, and as a result of pivoting, that this v21f becomes basic, and v21, A3 becomes a non-basic variable. Okay. Now at this point, all the what happens? So at this point, you see all the variables are within their bounds. Okay, so the normal simplex procedure would have terminated. But now here you found a solution to this over approximated LP instance. But now you have to check if the ReLU constraints are satisfied. Okay, and as you can see, this assignment, the satisfying solution, breaks a ReLU pair, specifically this ReLU pair, which relates v21 to v21, the v21 ReLU node. Okay, that relates v21 of f to v21 of b. As you can see, v21 of f is 0.5, but v21, the assignment for v21b is 0. Okay. And and v21 of f has to be max of these it has to be the max of 0 and v21 of b, and therefore so that is not the thing, and therefore that it is broken because v21 of is not equal to max of these things. And how do you fix this? Here, this is fixed by introducing a new update rule. Okay, so whenever ReLU pairs are broken, and if one of the either v2, the backward or the forward variable that form the ReLU pair are non-basic, then you will fix them so as to make this condition get satisfied. Okay. In this case, I'm choosing to fix the backward one, because that is the only v2b is non-basic. Okay. So v21 f has become basic. Therefore, I fix v21b by setting it to 0.5. Okay. Now, but that makes A1 go out of bounds, because A1 is dependent on, v21 of b changes, and therefore to 0.5, and that will, so A1 is no longer 0. Okay. Because this equation is violated. Okay. And that is fixed by pivoting A1 with v21 of b. Okay. I'm sorry, pivoting A1 with V11, I guess. Yeah, with V11. Okay. And this is the result of the pivot and update. Just one moment. Let me continue. Yeah. Yeah, Ganesh, an upload call pandren. Half an hour on. Okay, so this is as a result of pivoting, and yeah, so V11 now becomes 0.5. Okay, yes, and yeah, so now everything is okay. So A2, what happens? So make A1 goes out of bounds. So pivot A1 with V11. So A2 now gets goes out of bounds. So you pivot A2 with V21 of B, I guess. No? So I can't read. Yeah, V22 of B. Okay, because A2 is dependent on that, and that is we choose to pivot that with that, and so because that is A2 is now basic and it is out of bounds. So after pivoting that, you get this. Okay. So A2 now is brought back to 0, and V22 of B is set to minus 0.5. So at this point, all the variables are within their bounds. Okay, and all ReLU pairs you will see are also ReLU constraints are also satisfied. Look at V21 of F and V21 of B, both are 0.5, and V22 of B is minus 0.5. Since that is negative, V22 of F is 0. So all of them are thing, and therefore you terminate ReluPlex with success. So as you can see in this case, no case splitting was needed at all. And why is this the case? Because, so there can be several situations. In this case, with this condition V2, 1B being greater than or equal to 0, all permissible input values, and the problem is sat just by considering this case alone. Okay, so you never needed to consider the other case, because with that input constraints, it was enough. There was a solution. Okay, with just V2, 1B. The input constraint and the output constraints were such that this case alone allowed you to do. So either there is a satisfying solution in a single case, or maybe there are satisfying solutions, same satisfying solution in both the cases when V22B is V21B is greater than or equal to 0 or less than or equal to 0. In all such cases, if there are satisfying solutions for the problem, the property that you're trying to verify, then this will be a winner. Okay. Whereas if you use an SMT solver, maybe the SMT solver could have avoided this case split as well. But it entirely depends on the SAT solver heuristics that is used. And the SAT solver heuristics are usually they are generalized, optimized to handle all kinds of propositional structures, and not this limited propositional structure that a ReLU constraint imposes. Okay, and therefore, since it is optimized to solve the general problem, it may not always optimize the number of case splits that it requires. And by extending, taking care of this need to propagating these constraints lazily within simplex itself, you're able to reduce in a lot of cases the number of case splits. As I said before, this problem, even with ReLU, is NP hard anyway. So worst case, it is worst case exponential. Therefore, ReluPlex can also end up requiring all the case splits, but ReluPlex appears to perform much better on DNNs with ReLU when compared to general SMT solvents, and that's where the interest in ReluPlex remains. Okay, so any questions on this explanation that I've given you? Yeah, on the illustration. So then I will move on. Okay, so here are the additional rules. This ReluPlex has all the original set of simplex rules that I showed, the update and pivot. Additionally, it has two update rules, one for updating the backward node in a ReLU pair, and one for updating the forward node in a ReLU pair. Okay, so as you can see, if xi xj is a ReLU pair, okay, and xi is non-basic, the backward node is non-basic, and if that ReLU pair is broken, that is, it does not satisfy the ReLU constraint, then you basically, what you do is, where this is applicable when alpha xj is greater than or equal to 0. Since these updates are applied only after you run the LP, and the LP ensures that all the forward nodes, the value assigned to the forward nodes, are greater than or equal to 0 anyway. That is that it ensures, and therefore this condition is kind of superfluous. So here you just this update operation looks here a little bit complicated because it basically boils down to I haven't shown you the exact way in which the update is defined in the paper, but it just makes the backward node take on the same value as the forward node in this case, because alpha xj is greater than or equal to 0, and in that case, it fixes that by making xi take on the same value. Now, the other case is when the forward variable, corresponding forward node, the forward variable is non-basic. That is when you, if it's non-basic, because it follows. You remember that the update rule of the original simplex is applicable only, can only update non-basic variables. Okay, and that condition is followed here as well. So you update to fix the ReLU pair only if either of the backward or the forward variable corresponding to the ReLU pair is a non-basic variable. So in that case also, you just set the you bring the two things to be equal. In this case, there are two cases. Okay, one, if xi is a negative, then you will have to set it to 0. Xj, the forward variable, has to be set to 0. But if the input is positive, then you will have to make it equal. Okay, and that's done by this update operation, which kind of computes the delta required in order to bring xj to make it satisfy the ReLU constraint. Now, there is a special pivot rule also corresponding to thing, because sometimes as you do this, this updating and then keep repeating the LP, you can end up with a situation in which both the forward and the backward variables corresponding to a broken ReLU pair is basic. Okay, if neither of them is non-basic, then and the ReLU pair is broken, then you can't. Neither of these update operations is applicable. Therefore, you might get stuck. The ReluPlex might get stuck in the step where you may not has to fix the broken pair. Okay, the broken ReLU pair. So, in order to ensure that you can make progress in that step, which was actually step 3 in the procedure, I'll show you the procedure again. So then you may need to pivot one of the forward or the backward rules, which are both basic, become such and move them to make non-basic, so that you can update them to you can apply these update rules to be able to fix the ReLU pair. That's what is done here. So if an XI is a basic and happens to be an input ReLU node, then as long as there exists some, there's some pair, there is some output corresponding to it, and you can pivot it with any non-basic variable xj. Okay, whether they are the same pair or other things, you could, or any other variables that are not necessarily part of the ReLU pair. So this allows you to break out of the situation where both the forward and backward variables corresponding to a broken ReLU node are basic. So then you can flip, you can pivot it. Okay, unlike the original simplex rule pivot, this does not change the value. Okay, so I mean, it changes the value. I mean, in the original pivot, okay, it only changes the obviously it will have effect on changing the equations. Okay, but so it's like an update. After that, you'll be able to apply any of the update operations. Okay, and then there is a splitting rule, which which is needed only after you have exhausted applying all these three rules. Okay, and the success rule is also changed. It not only has to ensure that all the variables are within their bounds, okay, which is what the first condition here requires, and also all the ReLU pairs, okay, in the network satisfy their ReLU constraint condition. Okay, only then you will proclaim that it is a satisfying solution. Okay, so that is what thing. So I will, yes. Okay, so what is the terminating strategy for application of thing? So this is the same kind of a strategy that I showed you earlier, a little bit more systematic here. The said you repeatedly fix, you start with the over approximated LP instance where you throw away all the ReLU constraints, keep, then you repeatedly fix outer bounds violation on all variables using the standard simplex rules until a solution is found. Okay, if no solution is found, you can declare unset. Okay, if a solution is found, Then you have to check if any ReLU node, the ReLU constraint of any of the ReLU nodes is broken. If none of it is broken, then you have found a satisfying solution, the same solution. If there are violations of ReLU constraints, then you correct them by using update F or update B, okay, as the case may be, and using pivot for ReLU as required, okay, because there are situations where both the forward and the backward node can end up being basic. So in that case, you'll have to do. So then you keep repeating it. And if the ReLU correcting step, that is step 2, does not introduce any new outer bound after you correct all of them, if they do not introduce any new outer bound violations, then you have been able to successfully fix all the ReLU constraints. And then you will say, note here that you're not making any LP call at all. All you're doing is applying update F and update B and maybe pivoting without actually using any of the original LP rules, the simplex rules. Okay, there's no P calls. Then if you're able to do it, then you return SAT. What if this step 2, there is a possibility that this step 2 may not terminate, okay? Application of simplex LP always terminates, as we saw, okay? As long as you use a total ordering on the variables. But there is no guarantee that this fixing step of updating the forward and backward nodes, that may end up, violating. You may end up never being able to fix the thing, because here you're updating based on not on LP calls, but by just fixing the ReLU constraint. So it is possible to end up looping here. So that's why. So what this basic terminating strategy applies is it iterates in this step 2.1 a fixed number of times. Okay, if the correcting step has been applied, if it has been applied more than a fixed bound n, it usually happens when the same ReLU pair ends up breaking over and over again. Okay. And that is what you keep a count of. Then and only then you split it. Okay, you split the problem into two LP instances, and you go to step. If you keep repeating, then you have to go to step 3. I'll show you what step 3 is. And if you go to step 3, then you split it into 2 LP instances, and you have to apply this entire procedure to those 2 things. If the correcting step, if this terminates, the correcting step after a few iterations, if it terminates, but it introduces new outer bound violations, then you have to go to step 1. Okay. Before case splitting, if it introduces new violations, then you have to call LP again after fixing the thing. But if you have exhausted the iteration certain number of times and still you're unable to fix all the ReLU constraints, then you split it into 2 LP instances on a selected LP. So as you say, as I pointed out earlier, so each time you split, you will be creating 2 LP instances. Okay, as I showed earlier, and I will show it again. That's the slide that I skipped. Okay, here. So the splitting step. Okay, for example, here, suppose you tried. Okay, in this case, the ReLU pairs are not broken, but just for illustration, if you want to split an LP instance, which is an over approximation, into two refined LP instances, you pick a variable. Normally, you do that only when if you know you haven't been able to fix it, fix that pair, and then this is into two cases. One where that backward variable is less than or equal to 0, and the case where the backward variable is greater than or equal to 0. Okay, and each of those cases can be considered separately by, and you can create an LP instance for each of those cases. If V2B is less than or equal to 0, then you take that into account by fixing the upper bound of V21 of B, which is what I've done here. And if V21B is greater than or equal to 0, then you fix this. And then in this case, you have to create an equality, because if V21B is greater than or equal to 0, then you have to add the constraint that V21 of F must be equal to V21 of B. Okay, and for that you will introduce a because for that you need to introduce a new additional variable in order to model it as an LP. So this is how you split the problem into two LP instances. Okay, so that's how go back to yes. Okay, yeah. So I will end my part here. Okay, so maybe I went. Yeah, any questions? Okay, we went a little bit too fast. I mean, if you don't have any questions, I'm sure that you need to digest this thing and then ask. So what I will do is, I'll give you some exercises. You'll have to take some examples and then new examples which I will make. And I really want you to kind of simulate it both on the original simplex as well as the ReluPlex, and try them out on the on SMT solve, invoking them in some solver. That's when you will really understand, and you may have some questions. I would more than encourage you to come back, listen to this lecture, and get your doubts clarified if you have any questions. Okay, that comes later on. Okay, so I'll stop here. My part. So what do you want? What do you guys want to do? Okay, I said. So I've taken more than 6:30. Okay, so what do you want to do, Diganta? So do you guys want to take a break for 10 minutes or?
I think.
Yeah, break would be better.
Yeah.
Yeah. So let's assemble at 7 o'clock, and then you go till 7:30.
Sure. So I'll maybe only do a little, like say a little less than half of my part, but let's do that.
Yeah, you stop it at whatever logical part that you.
Yeah. I'll skip that. Yeah. Okay. Hi, are people here? Hello.
I'm here. Only two other people. But I think even if there are one or two people, you should, or you want more people, you can start next time also. Is it there?
Yeah, what would you
Hi,
suggest, sir?
Digandar.
Yeah,
I'm-
Soham?
yeah, I'm here. And Rohan and Ashutosh are also here. I mean, their mics are,
Okay.
Oh, you have, yeah, I forgot those things. Okay. Yeah, Rohan is here.
Right. Drew.
I
I
think
think
we have enough people. Let's go ahead. Yeah.
yeah, sure. So I'll start screen share. Can you make me co-host?
Yes.
Okay. So is this visible?
Yeah.
Okay. So I'll basically quickly. So what I want to do is talk about this particular,
By the way, before you do that, there's one point. If they want to, I might want to give some exercises. Both kind of some thing where they can use Reluplex on some small examples. And Marabou is the
yeah, I think Marabu is the way to use it. There was this one, so the assignment that will have some Z3 exercises there in the Madhukar's assignment that we had.
I think the one that I've given them as thing. Okay, the second problem. Oh, they can actually, you can make them use Reluplex as well as an SMT solver and then compare, no?
Yes. I think
okay. So let's do that then. Yeah. So I will modify the thing. Maybe also want to add a few theoretical questions. I mean, questions that will force them to kind of simulate simplex and the thing, so they will understand. So, but anyway, that's my thing. So, yeah. Okay. Good. Yeah. Go ahead.
Yeah, so I want to talk about this one particular method of neural network verification. So this is done by some people at ETH Zurich. Okay, let me just look at the names of the people involved here. Yeah, so there is a really good team at ETH Zurich which are looking at neural network verification. So these people are have done this work. And this is basically, it uses some over approximation based techniques to try and do the verification in a more scalable way. And I'll maybe not be able to get into the details of the technique, but I'll at least maybe be able to motivate why we need over approximation and what sort of over approximation in a neural network context means. So what they do is they use something, or they borrow a term from program analysis called abstract domains, and they use that in this neural network verification context, and I'll explain that from a neural network verification point of view. So in the last lecture we looked at Reluplex, right? Like just now. So Reluplex is a decision procedure which is essentially based on solving, right? So what we do in Reluplex is, we are always carrying specific values of the variables. So whenever you have that LP instance, then you're doing some solving, or you're passing this to an LP solver. This will produce some candidate values of variables, and then you try to see if you can make the ReLU constraint satisfiable with those values. If not, then you adjust the constraints and so on, right? So essentially, at a high level, you can think of the Reluplex algorithm as iterating over possible satisfiable values, right? So simplex is also doing that in some sense, right? So each sort of state in the simplex is one of the possible vertex position, which represents one of the possible states of values or set of values that we want to look at. So even Reluplex in some sense is doing that. It's iterating over values, right? And it will keep doing this for a long while. And if it fails, then it will do a case split, right? So in this sense, ReluPlex is actually working with the exact network. It carries, in some sense, the entire information of the network, right? So it does not, in any sense, introduce something like set of variables or anything like that, right? It carries the exact values of the variables. It might be true that those exact values might not happen in a real network, in the sense that not all the ReLU constraints are satisfied, but nonetheless, it's one set of values for all the variables in the network. So if we have some network like this, as Sir was saying, at each point in the ReluPlex algorithm, you have some value for this variable, some value for this variable, some value for this variable, and so on, right?
And one place I kind of disagree is it does compute the set of possible values there, but I guess it computes the set of all precise values. Okay, I mean, but it doesn't consider one value at a time. Is that right? So that's.
No, so even when, so what I mean when I say it considers one value at a time here is, even when it's doing the iterations, it is doing some LP.
That's true.
And that, yeah, so inside the LP, it's just using simplex, and that is considering one.
That is true. That is true.
Right. And then we fix one of the ReLU constraints. And then, even there, we're just, setting the values to be something, right?
Yeah, it's exploring assignments.
It's exploring specific assignments. So is this clear for everyone that we're actually just, iterating over some list of values?
Yeah, but that's finite. It turns out to be finite because it is looking at those intersection points or subset of intersection points, but still large set.
Yeah, it's still a large set. Yeah,
you're exactly right. Yeah. Sorry.
So I mean,
is that clear? So that's important. Yes. Okay. So yeah. Okay.
Yeah. So just to maybe emphasize this a little bit. So in simplex, the situation was this. So your simplex, you're looking at again you're iterating over some finite set of values, and the reason why that is enough is because what you're trying to do is you're looking at whether or not there is some point inside of a polyhedron. So it suffices to look at only the intersection points of the various planes or the various constraints that you have, right? In ReluPlex, you're still looking at finite sets of values. So you still have some set of linear constraints coming from the linear layers, and you have some ReLU constraints, right? And you're still basically looking at one particular assignment, which will basically mean that you're at the intersection point of all the linear constraints, and some of the ReLU constraints are actually satisfied, and some of them may be unsatisfied, right? And then you try to see if you can get to a point where all your constraints are satisfied. So you're still going over, in the similar way to simplex, you're still going over or iterating over set of values. And similar to how in simplex we saw that it's like the system or the algorithm terminates because it's sufficient to check only finitely many possible precise values. In a similar way, ReluPlex will also terminate because it's sufficient to check only finitely many possible values. If you do this,
there's only one constraint that it has to make. Okay, this fixing can go on, can repeat forever, but
so we'll have to do some splits.
Yeah, the splitting has to be done.
Yeah. So if we do the splitting, then definitely, at the end of the day, it will go over some large set of values, but it will terminate, right? But the point that I want to emphasize is that it is actually iterating over some finite set of exact values of the variables, right? And the other thing that ReluPlex needs to do is that whenever it needs to do so it doesn't always, it is not necessary that it may need to do this, but whenever it needs to do a case split, what it's essentially doing is analyzing each case of the ReLU separately, right? So if, for example, there is this one particular ReLU, so if there is this one particular, so let's say that there is this network and it ends up splitting on this particular ReLU, right? So if it ends up splitting on this particular ReLU, that means it's basically doing a case split where it's analyzing the case where this ReLU is going to be set to inactive phase, and the case when this ReLU is going to be set to active phase separately, right? So it analyzes, in some sense, it analyzes each case separately. So this is actually not, it turns out it's not very efficient because A, you might need to iterate over a very large set of values, as we're saying, right? Potentially exponentially large set of values. And B, there might be potentially it's wrong. It should be exponentially, not. Yeah, yeah, yeah. It's not infinite. There may be exponentially many case splits, right?
Yeah, in the number of nodes, yes.
Yeah. And even the possible set of values that you basically end up iterating through can be exponential, right? So is this clear that, we are iterating through sets of values, but, iterating sets of values and doing some case splits, but there can be exponentially many case splits and there can be exponentially many values that we need to check before we can completely eliminate all possible satisfying assignments. Is this clear to everyone?
Yeah, worst case exponentially. There might be, yeah.
Yeah, worst case exponential, definitely. So any questions so far? Is this clear? Because this is, at least if you don't at least understand this at an intuitive level, it really doesn't make much sense why we need to do over approximation and why we're going through, the motivation behind the next bits won't really make sense. So this is, important in the sense that if you don't understand anything over here, please say something. I realize I just saw the algorithm, but still.
Yeah, if there is some confusion about, I also talked about over approximation, the LP instance that you start with in the ReluPlex before you do the case split is an over approximation because it assumes there's no relationship, the max relationship between these two, forward and the backward node, it throws away. But that's a different kind of over approximation. But as he said, that eventually it may have to, when you do a case split, you are throwing back, you're refining that over approximation. Tries to see if it can solve, it can find a satisfying instance even without those case splits. But maybe that will happen, maybe that will not. Okay, but the kind of over approximation that I guess deep poly you will talk about will be different on considering the set of values as you explore itself. Yeah.
Right. So it'll basically, instead of dealing with single, a single assignment, it will try to deal with set of possible assignments. Okay. So this is basically the idea that here in ReluPlex, what we're essentially doing at the end of the day, is dealing with single assignments. So you look at one particular point and you eliminate that as a possibility. So this is not a satisfiable point. Then you move on to say another point and you eliminate that and so on. And it turns out that this is actually, you can get away with only looking at finitely many points, right? But you are doing this one point at a time. And that, as I've been saying, that is not very efficient or scalable because the number of points you'll have to check, which again corresponds to the number of case splits you'll have to do, that is exponential in the number of nodes in the worst case. And it turns out to be that way for many networks. Like ReluPlex often takes a lot of time, even on small networks. So for this reason, this does not scale, right? And what we instead want to do with over approximation based methods, what they try to do is that they, instead of taking a single point, they want to take a set of variables. They want to take an entire set of points and see if you can deal with entire set of possible assignments at the same time, right? So remember, what we're trying to solve is basically a SAT problem, right? So we have some some property that we've been given to us. So, or maybe I'll write it in this way. So we have some precondition and we have some post condition, and we want to see whether if any input is in some precondition, whether the post condition is ever violated, right? So that means that we'll have some bad region where, if you find any point inside the bad region, in which all the constraints of the networks are satisfied, then we know that that point is a counterexample, right? So even with Reluplex, when we actually use Reluplex, this is how we are going to use it, right? We're going to give Reluplex or the network, and it's going to use derive some constraints from the network. And we're also going to give it some definition of a bad region as a polytope, right? And we're going to ask, is there some point which satisfies the network constraints and is inside the bad region? Because then that would mean that that point is a counterexample, right? And that your property actually does not hold. But if you can show that actually all your points are outside the bad region, then you're done, right? So Reluplex is going to go point by point. Here in over-approximation based methods, what we're trying to do is we again have some bad region, and we'd again want to show that, let's say if the actual concrete behavior of the network was something like this, this region represents all the points. So point here basically means values for all the variables at all the layers and so on, right? And this region represents all the possible behaviors of the network. And you're trying to show that this behavior region does not intersect with the bad region, right? So what over-approximation tries to do is that instead of going one point at a time to cover this entire behavior region, it will try to take sets of points. So it will take a set of points, some set of points like this, and then basically see whether that set of points ever intersects with the bad region or not, right? So what over-approximation will try to do, or over-approximation based techniques they try to do, is they try to find some set of points like this so that the actual behavior of the network is contained in that. And the bad region is does not intersect the set of points, right? So if you can find this blue space, and show these two things, one is that this blue actually contains all of the actual behavior. And if you can show that this blue region does not intersect with the red region, right? So if you can show these two things, then you have proven proven the fact that there is no bad assignment, right? You have proven that there is no violation to your property. Your property has to be correct. So this is what the over-approximation based methods try to do. They try to find these sort of blue spaces, and they try to see whether it intersects with the bad region or not, right? So why do we do
this? This is kind of comparable to, earlier in programming examples, I showed you how intervals could be pushed from one statement as predicates, how they can be pushed, and interval constraints can be pushed. Okay, so that's what you're talking about, isn't it?
Yeah, exactly. And I'll get to that precise example. I have an example where I do interval propagation on the network.
But it's 7:18. I want a hard stop at 7:30, I think.
Yeah. So I'll just talk about this slide and maybe just show the interval example. That will not take too much time. But yeah, then I'll stop. So okay, so as I was saying, over-approximation is going to deal with sets of variables. And this has some advantages in the sense that it actually allows us to handle multiple cases simultaneously. So for example, here in each one of these points, we basically have fixed the activation of all the ReLU nodes, right? So whenever we're eliminating one point, we're eliminating one possible combination of activations for the ReLU nodes, right? But here we can actually, if we can find this good enough blue region, we can actually eliminate multiple such combinations of activations, right? So you've got these 2 points. You might have a node which is actually active in this particular point and inactive in this particular point. But when you're taking this blue region, you're covering both of those points in your analysis. So it can handle multiple cases simultaneously. And of course, it's not going to carry the entire information of the network in the sense that it's not going to carry exact values, because that might be more efficient in the sense that carrying the entire information, carrying exact values might be wasteful. The downside of using over-approximation is, of course, that it can lead to false negatives. So what can happen is a situation like this can happen where you have a red region. Sorry. where you have some red region, and maybe the exact behavior of the network does not intersect the red region, right? So the network is safe, but the blue region you end up finding does intersect the red region, right? So in this case, with over approximation based techniques, by default at least, in this case, you can't really say anything. Because remember, you don't know what the actual, exact behavior of the network is, right? All you see is that you have this blue region and it intersects the red region. But you know that it's definitely possible that the black region still does not intersect the red region. So the precise behavior is still safe. It's definitely possible. Or it's definitely also possible that the precise behavior is still unsafe, right? So in this case, this might be the situation, or this might also be the situation, right? So you don't know whether, which of these two situations there is, right? So then you can only give out what can be called as a warning, or what can, end up being a false negative, right? So you can maybe pick a point from this region and say that, okay, look, this might be a counterexample to the property, but it might also end up being a false negative, okay? So yeah, so I'll just take 5 more minutes. I'll try to show how you can do it with intervals, how you can actually do some propagation through a network with intervals. Okay, so let's say that we have this network, and we have the input properties is going to tell us that both this x1 and x2, they lie in some interval which is -1 to 1, right? So now, whenever we do this sort of set-based approaches over approximations, what we have to always fix is some representation of the sets, right? So you can think about various ways to represent sets. Of course, you cannot represent sets as just lists, because there might be infinitely many points here. You have to be a little bit more clever, a little bit more symbolic. So you might try to figure out some symbolic template sort of a situation with which you can represent sets. One example of such a representation is interval. We call these representations abstract domains. And as Sir showed, you can push intervals through statements, right? And we call this sort of push, whenever we push these intervals, or we push these abstract domains through statements, we call this the abstract transformation, okay? So essentially, you have some actual operation. So that may be a linear layer, let's say, right? So you have some actual concrete operation which takes a variable to something here, and this is going through a linear layer, let's say. But now what we're saying is that we're not looking at variables, we're looking at sets of variables, right? So there is a connection between here to, let's say, some sets of variables, right? And you can also think of this linear layer as being lifted to the space of sets, right? Like you can just take each point here to each point here. You can think of that, as something that happens, but arbitrary sets might be hard to represent. So we choose some particular sets like intervals. Of course, an interval is a set, but all sets aren't intervals. So we choose some particular sets that we can represent like intervals and call these our abstract domains, right? And then if you have some linear layer, or if you have even some arbitrary function, let's say f, right? If f takes some x to y, then you can sort of think of a set of values of x, and f will take that to the image of this particular set, right? So it will take to this particular image under x. Now, you're not actually looking at arbitrary sets, but you're looking at intervals. Then what you can try and see is, you can see, okay, where will this interval go to under f? It might go to some arbitrary set, but you find the largest interval that will contain this in some sense, right? And this is the basic idea behind abstract transformers, where you try to take the precise action which f is doing, and we might call this f dash. We try to take the precise action that f is doing and try to make that act upon the interval. And whatever we get on the other side, we try to fit a tight interval to that, right? So you might have some, complicated function that takes x to, somewhere else, but you apply that function on all of the elements of an interval, you'd get some set over here. And you try to find an interval which contains this set and is tight in that sort of way. Okay. So this is the way you can do some abstract transformation. And this is basically exactly like what Sir was saying in terms of pushing intervals through, right? So I'll go over this in a little bit more detail next class, but I just want to give you the example right now in terms of pushing the interval through the network, if that's okay. So if you remember, we had -1 and 1 over here, right? So we know that this x1 is contained inside -1 and 1. We also know that x2 is contained inside -1 and 1, right? So these are the set of values for x1 and x2 that we're tracking. Okay. So now we know that x3 is going to be the sum of x1 and x2, right? So what can we say in terms of what is an interval which x3 must lie in, right? So see, the minimum possible values of x1 and x2 is -1, right? So the minimum possible value of x3 is going to be -2, and that's going to happen when both x1 and x2 is -1. Similarly, the maximum possible value of x3 can happen when both x1 and x2 is +1, that is 2, right? So this is one situation where you have -2 to 2. And similarly, for x4, again, what is the range of values? Can someone tell me? What is the range of values x4 will lie in? Hello? Okay. I think it's too late for. Yeah. Okay, I'll just say. So again, like you can go back and check this. I'll just say this right now. But yeah, you know, again, x1, if x1 is -1 and x2 is 1, then you'll get the minimum possible, and that will be -2. Similarly, the maximum possible will be when x1 is 1 and x2 is -1. So that will be 2. Okay.
Right, got it. Yes.
Yeah, so I think it's kind of late, so I don't have too much time. So again, if you pass this interval through the ReLU, so I'm saying that, okay, before the ReLU, the input to the ReLU is between -2 and 2. What will the output be? So if the input is in the negative side, it will always just get 0, right? So anything, you know, if this is your interval and this is say 0, any of the inputs over here will just map to this point 0, right? And any of the outputs here just stay where they are. So the minimum value on the output side is going to be 0 itself, and the maximum value is going to be whatever the maximum you had. So in this case, it will go from 0 to 2. Similarly, over here also, it will be 0 to 2. And again, you're adding up two values. Both of them are going from 0 to 2. So the minimum value will be 0 plus 0, that is 0. Maximum value will be 2 plus 2, that is 4. Okay. So is this clear?
Yes.
Okay. Yeah, I'll go over this.
Yeah, one other point is that this may, like in this case also, -2, 2, it includes certain values that is not permissible. Right? I don't know if maybe in this case it does. In general, certainly, it may include when you propagate these things. In this case, 1 is not possible here, but it includes 1 possible.
1, yeah, I think so. 1 over here, for example, is possible. You can have x1 to be 1 and x2 to be 0, for example, right?
Because you're including everything. So maybe here it is precise. Okay.
No, it's not precise actually. So
well, what value? Can you tell what value?
Yeah, in fact, the 4. So, for example, the interval we get over here.
Here I understand. In the first layer, it is.
Yeah, in the first layer is precise. In the first layer is precise.
Yeah, first layer, the linear transform makes it precise, but the ReLU will introduce imprecision.
Yeah. The ReLU will always introduce some imprecision
because the two cases will be merged. Yeah. So I guess you guys need to understand those kinds of things. Yeah.
Yeah, I'll go over this in a better way next time.
What I mean, I think that we need to plan some exercises, okay, and force them to do it. Okay. So
yeah, definitely. But I actually had some nice examples here about the interval domain and some values being contained versus not contained and so on. So maybe
Yeah, I think let's do this. Let's take it, easily. So
Yeah. So
yeah,
maybe next time I'll show it because it's already 7:30 right now.
yeah,
Yeah. But yeah, so this is the interval that you get, and it's not a surprise that this interval is actually too large to prove your property. The property was that x7 should be less than equal to 3. This should be less than equal to 3. And this holds. We'll show this next time. But turns out interval propagation is not sufficient. So anyway, I'll go over this next time.
Yeah, I think this is a good introduction. So hopefully, yeah.
Yeah. So I'll ask you one of these things. Like, look at this network and see if, like sir was saying, see if there is some value. So for example, we're saying that x5 is in this interval, x6 is in this interval, x7 is in this interval. Is some combination of values for these variables being introduced when we're saying that each one of them is in these intervals, which is not actually possible in the network? So in the next class, try to find out some value of x1, x2, x3, x4, x5, x6, and x7, which are in these intervals for the corresponding variables, but which is actually not possible in the original network, in the sense that, the original network will actually not show that value ever. So try and find that out. Okay.
Yeah.
Okay, sure.
Okay.